Any questions?
دكتور انا ما ضبطش معي الهوم ورك فما سلمته. قديش بنحسب هو بالله عليه بس؟
احنا راح يكون عندنا 5 homeworks 5 homeworks راح يكون فيه ان شاء الله.
تمام.
فما بعرف كيف نحسبهم، بس ليه ما زبط معك؟ يعني ما زبط معك السبمشن؟ ابعت لي ايميل.
طيب خلاص اوكي.
برضه ليث الزعبي ليث ما وصل على السيستم. بعثت لك ايميل انا، انت سالتني انه اشيك لك، كان عندك مشكله في الانترنت، فبليز send it to me as a PDF file عشان ابعتها للتي اي بليز.
تمام.
دكتور
ايوه
انا ما لقيت السؤال اصلا، ما فهمته.
اي سؤال؟
اللي هو تاع الهوم وورك، فما حليته، يعني ما لقيت سؤال.
كيف ما لقيت سؤال؟ يعني في لينك جوا لما تكبس على هوم وورك 1 بيطلع لك فيه فايل، تكبس عليه بتسوي له داونلود، تفتحه موجود الاسئله فيه.
هذا غريب، ما طلع لي، يعني ما بعرف.
لا لازم يطلع لك يا عبد الله.
طيب فممكن
اذا في وقت في اخر المحاضره بوريك كيف.
خلص تمام، لان انا عن جد ما لقيت لينك وما ما حليته، فمش عارف.
اللينك موجود، بس انت لما تكبس على هوم وورك 1 بيطلع لك لينك لفايل، تكبس عليه تسوي له داونلود او اوبن، مكتوبه فيه الاسئله والمطلوب منك. اللي موجود على الاي ليرنينج هو الجايد لاينز كيف تسوي سبمشن، وفي لينك الفايل نفسه.
تمام، بس عشان توريني دكتور اخر المحاضره.
هذا في مجال ان شاء الله. ان شاء الله. اوكي. طيب احنا last time we started chapter 4 which is about combinational logic circuits from two perspectives, analysis and design. We talked about what is a combinational logic circuit. We said basically it is a logic circuit with a set of inputs and a set of outputs. And the main thing about such type of circuits is that any output of this circuit is only dependent on the current input value or current input combination, and hence, and that's why these circuits are called combinational logic circuits. We discussed how to analyze a combinational logic circuit. In other words, given some logic circuit, some combinational logic circuit, and with some inputs, some outputs, what is the logic expression that maps the input to the output? So this is called analysis, and we discussed only one example because we said this is kind of straightforward. We talked about it earlier, and there is, I ask you to check the slides. There is an animated example where you can have more practice on it. The second thing we started talking about is the design, in which we said, given the description the description of some combinational logic circuit, we want to design it. In other words, we want to find the logic expression that maps the inputs to the output or outputs based on our understanding of this description. And we said, basically, we have a few steps. We need to, based on our understanding, we need to determine the number of inputs, the number of outputs, and based on our understanding of the problem statement, we have to find the truth table. And once we have the truth table, we can easily find the logic expression that maps the inputs to the outputs. We can find it as a sum of min terms. We can find it as a product of sum of a product of max terms, sum of product, or product of sum. In other words, we can take it as is, as a product of sum of min terms or product of max terms, or we can simplify it as a product of sum or sum of a product. So this is what we discussed last time. And chapter 4, the majority of chapter 4 is basically related to the design. We took few examples last time, I think 2 or 3 examples. Let's take few more examples, then we move to other specific design problems where we will design common functions that you usually need when you design combinational logic circuits. So, but still it is a design, they are design topics. So let's take 1 or 2 examples. So example design a BCD to XS3 converter. So we want to design a circuit that converts a BCD, and let me be more specific, a single digit BCD value into its equivalent BCD XS3 code. So this XS3 code is basically a type of binary code. If you remember in chapter 1, we discussed few examples on binary codes such as ASCII, Unicode, and so on. And this XS3 is basically one type of binary code. So we want to design this circuit, and that's it. You see here the problem statement or the description of the circuit is not as straightforward as the examples we discussed last time, where we, from the problem statement, it was clear what was the number of inputs, what was the number of outputs, what is the relation between the input and the outputs. Here, it's kind of implicit. So we need to have a better understanding of this statement in order to specify the number of inputs and outputs. So what is BCD, a single digit BCD? So this is the input basically. It converts BCD to XS, and this is the output. So this is the input and this is the output. So now we need to know what is a single BCD digit, how many bits are, or how many inputs represent a single BCD digit, and how many bits are or outputs are required to represent the XS3 code. So basically, we already know the BCD numbers. We know a single BCD digit is how many bits. How many bits you need to represent BCD number?
4 bits.
4 bits.
Yes, Sarah. So this is, here we have 4 inputs. And these 4 inputs represent a BCD digit. We are familiar with the BCD. So let's call these inputs, for example, A3, A2, A1, A0, where A3 is the most significant bit of the number and A0 is the least significant bit. How about the output? In order to know what is the number of outputs, I need to know what is XS3 code. Basically, XS3 code, this XS3 code is from its name. It is XS3, which means plus the 3, which means it is BCD plus 3. And that's it. It is BCD plus 3. So if I know this fact that the XS3 code is essentially the BCD digit plus the 3, how many outputs do I need here? What is the minimum?
7?
7? No.
5.
5, Abdullah. No. How about 4? Why 4?
ما بيصير overflow.
Why 4? Let's check. For BCD numbers, for a single digit BCD number, what is the minimum value? It is 000. What is its equivalent XS3 code? It will be this plus 3, so it will be 011. 0001 will be 0100, and so on. What is the maximum BCD value? What is the maximum value that I can store in a single digit BCD?
9.
9, exactly. It is 9. So it is 1001. So the maximum value that I need to represent XS3 code for 9 is 12, which is 1100, right? What if the input is 1010? What is the XS3 code? This input as a BCD value will never happen, right? Because the maximum value for BCD is 1001. So the output here will be don't care. The same thing for all values up to 15, we will have what? Don't cares. we'll have don't care. So basically, how many bits do I need at the output? 4 bits. Let's call this output 3, output 2, output 1, output 0. So now we need to design the circuit. What is inside this box based on this understanding? We know the inputs, we know the outputs, we know the relation between the input and the output, which is BCD plus 3, or the input plus the 3. If this was a binary value, a normal binary value, standard binary value, what we will have here, how many outputs we will need? The maximum value will be 15 in the input, so the maximum value in the output will be 18. So we need 5 bits. So if in case the input was binary value, not BCD, then yes, we will need 5 bits because the maximum input is 15 and the maximum output accordingly will be 18, right? But here, because the input is BCD, the maximum value for the input is expected to be 9, which is 1001. So the maximum output is 12, which requires only 4 bits. So this is the inputs, the outputs, and the relation. What is left basically is to put the truth table. Based on this understanding, we need to put the truth table, and the truth table will be big because we have 16 possible combinations at the input. We have 4 inputs. So let's put here A3, A2, A1, A0. And here we have 4 outputs. Output 3, output 2, output 1, output 0. And it is straightforward. 0, 0, 0. The output is 0, 0, 1, 1. Which is basically the input plus 3. 0, 0, 0, 1, it is 4. 0, 1, 0, 0. 0, 0, 1, 0, 0, 0, 1, 1. So these are the possible input combinations: 4, 5, 6, 7, 8, 9, and these the valid inputs. These are the valid inputs. And the output will be this plus 3. 2 plus 3 is 5, 6, which is a 3 plus 3. 4 will be 7. This will be 8. This will be 9. This will be 10, 11, and 12. Right? How about 10 when the input is 10 and the input is 11? The output will be don't care, don't care, don't care, don't care. Same thing for the input 12, input 13. This will be don't care, don't care. Because these inputs are not valid BCD values. The same thing for 14 and 15. We will have don't care, don't care, don't care, like this. So now we have the truth table. And as we said last time, the critical part in the design is finding the truth table. If you have the truth table, then that's it. Okay, then that's it, because we know how to simplify the truth, any function if we have its truth table. So we have here 4 outputs. So we need to do 4 simplifications. We need to find 4 logic expressions, 1 for each of these outputs. I will do 2 of them only, and I will leave the rest for you. So the first one is output 3. So we have here the K-map, which is a 4-variable K-map. This is input A3. This is input A2. This is A1, and this is A0. So this is output 3. This is this column. Okay, so if we fill the map, it is 0, 0, 0, 0, 0, 1, 1, 1, which are 6 and 7. 8 is 1, 9 is 1. This is 8, 1, 1. Then the remaining are don't cares. So this is the key map for output 3. So if you want to simplify it as a sum of product, you will have this as a prime implicant, and you will have this as also a prime implicant, and this as a prime implicant as well. So we have 3 prime implicants, and all of them are essential, so we need to include them. So this output 3 as a function of A3, A2, A1, A0 is basically this prime implicant. What is this prime implicant? The big one. What's this one?
A3 Doctor.
A3, yes, it is A3, or this one. This is
A2.
yes.
A0.
A2, A0, or this one.
A1 or A2.
A2 and A1.
A1.
Excellent. So the same thing, if you do the same thing for output 2, output 1, output 0, and I want you to do that, you will get the following. Do it, leave some space and do it later. Output 2, output 2 will be, okay, let me just, output 2 will be A2 bar, A2 bar A0, or A2 bar A1, or A2 A1 A0 bar. This is A output 2. Output 1 will be A1 A0 or A1 A0 bar. Output 0 will be A0 bar. Okay, so these are the 4 functions for this circuit. Then you need to draw it using AND or invert gates, or you may draw it using NAND gates only or NOR gates only. We know how to do that. So if you have these logic expressions, also leave some space, draw the logic diagram using AND or NOT or invert gates. All right, so you need to draw a map for each of these output, a different map. Now, if you look at this one, output 1, what is this? A1 and A0, or A1 bar and A0 bar?
XNOR.
It is XNOR, yes. So this can be written like 0. This is A1 XNOR A0, XNOR A0. So you can replace all the gates in this expression with a single gate, which is an XNOR gate. Okay, so this is another example on the design. And as I said, we will take more examples later when we design specific circuits, but the concept is the same. You need to know the inputs, the outputs, the relation between the inputs and the outputs. In other words, the truth table. Once you have the truth table, it's over. You can do the simplification. All right, any question? Okay, I want to give you another example, but I will leave it to you to solve it at home later, but it is straightforward. Do it later. Design let me just, in order to give you the answer. Yes, design a circuit that accepts a single BCD digit and outputs 1 when the input value is greater than 4. Okay, so we want to design a circuit that accepts a single BCD digit and outputs 1 when the input value is greater than 4. So basically, we want to design a circuit. The circuit accepts a BCD digit, so the number of inputs, as we saw in the previous example, should be 4. Okay, so let's call these as we did previously, A3, A2, A1, A0. And the circuit, it outputs 1 when the input value is greater than 0. Otherwise, it outputs 0. So how many outputs do we have?
9 دكتور. انه اوتبوتس حيكون كمان 4.
ليش 9؟
انه فكرت هيك او 4 حيطلع.
Okay, we need to output either 0 or 1. How many bits do you need if you want to represent or output 2 values?
1 bit.
1. Yes, log of 2 is 1. So we need 1 output. And this output is 1 when the input is greater than 4. And it is 0 when the input is less than or equal to 4. So basically, if this value is greater than 4, the output is 1. So if you want to write kind of equation, this output is 0 when A3, A2, A1, A0 is less than or equal to 4. As a decimal value, if this decimal BCD digit is less than 4 or equal to 4, the output is 0, and this otherwise. Okay? Or if you want to write it explicitly, A2, A1, A0 is greater than 4. So given this and this and this, you can build the truth table, which will be 16, which will have 16 input combinations, and you will have 1 output, so you have 1 K-map, you will have 1 K-map. If you try to simplify it, you will find out that output is A3 or A2, A1, or A2, A0. So try to do it at home. You will need if you simplify as a sum of product, in other words, you take the ones of this output, you should end up with this logic expression. So leave some space to draw the truth table and the K-map and try to simplify the function to get to this expression. All right. Any question? So please try to do it. All right. Any question? Okay. So let's move forward in this chapter. We will now consider the design of other combinational logic circuits, which are basically examples on the design, but the circuits that we will design in this chapter, the remaining circuits, are very important. They are called functional blocks because designers usually use them as blocks. In other words, they don't redesign them from zero, from scratch whenever they need them. They just use them as blocks. But before we discuss them, I want to introduce few concepts. So let's say section 4.4, I guess. I will usually call it basic concepts. So these are some of the concepts that we will need later when we talk about the design of other sequential combinational logic circuits. So some of these basic concepts are as follows. The first thing is functions of single variables. It's kind of some definitions, let's say, and concepts, single variables. So if I tell you that you have a function f that is function of some variable, let's say w, what are the possibilities? This function is a function of one variable. What are the possibilities for this function?
Yeah, 0 1.
This function could be always 0, or this function could be always 1, or this function could be what? What else?
Zeta.
Zeta, no. Single variable as a function of w.
W or W bar.
It could be w. It could be the same as w, or it could be the complement
W
of
bar.
w, right? So these are the four possibilities that we may have for any function of a single variable. So we want to give them names. This is called, if this starts from here, if the function is the same as the input, we call it transfer function or transferring function. Transferring function. For this one, we call it inverting function, which basically because it inverts the input. This one, we call it value fix to 1, and this one is called value fix to 0. So it's kind of, we want to be familiar with these because we will use them later. When I tell you value fix the output to 0, you know that you need to set the output always to 0. Value fix to 1, you want to set the output always to 1. Transferring, inverting, we just want to be familiar with this terminology. Okay, so this is the first basic concept, which is very straightforward and simple. The second thing, or the second concept, is the concept of bus. Bus in digital circuit. What is meant by a bus in the digital circuit? Simply, a bus is a set of wires or a collection of wires in your circuit. So you have 2 or 3 wires, you combine them together and you call them a bus. Why you combine them? Because these wires are carrying bits, and these bits are related to each other, have some relation to each other in terms of representation. For example, you may have 4 wires like this. And this wire, for example, is carrying A3, this wire is carrying A2, this wire is carrying A1, this wire is carrying A0. So these 4 wires are carrying some value that represents one entity, some entity. So usually when we have something like this and we want to draw the circuit, it will be much easier to draw these like this as a single wire, and we put 4 here and we call this, let's say, A. So this notation implies that we have here 4 separate wires, and they represent some value which we call A, which has 4 sub variables, A3, A2, A1, 0. So sometimes we say we combine them into this bus. This is a bus into this bus like this. So it's kind of compact representation of these wires. Instead of working with 4 wires on my drawing, I just draw 4 wires, 1 wire, and put this tick and the number of wires inside this bus. We can always deassemble these wires by saying something like this. This is A3, A2, A1, A0. So what we are concerned with is when you see something like this on some circuit, you should know that this implies that we have 4 separate wires that were combined to represent in a single representation, which is a single wire to represent a bus. So this is a bus. You can combine, you can deassemble in this way. Okay, so we will see this notation frequently later. 4 wires, 8 wires, 2 wires, and so on. Okay, so this is the second thing, which is the concept of a bus. So in the computer system, you hear them usually tell you the data bus, the address bus, the control bus in your computer. So what do they mean by a bus? It's not like the bus that you ride. It is a collection of wires that are carrying one piece of information. Multiple bits that carry some piece of information from one point to another in your system. Okay, so this is the second thing, or the second concept. The last thing, or the last concept, which is very important also, enabling circuits. Enabling circuits. What do we mean by enabling circuits, and what circuits can we use for this purpose? Enabling circuits basically are those that can be used to either pass or block some input signal or value. So we have some circuit, some input, some output, and this circuit can be used to allow the input X, let's say, to pass to the output Y. So any circuit that can achieve such purpose, in which you can control or enable, the circuit such that the input passes through to the output, or it is blocked, it's not allowed to pass the output, is called an enabling circuit. And one popular example for it is, what type of circuit?
Tri-state buffer.
Yes, we're already familiar with it. So one example of such circuits is the tri-state buffer. The tri-state buffer is very similar to what I drew here. The tri-state buffer can be used as an enabling circuit because it enables the input X to pass to the output Y using this control or this input. However, the tri-state buffer has one little issue, which is when C is equals to 0, or the enable is equal to 0, the output, the value of the output is not specified because there is a very high resistance here which prevents X to pass to Y. So this is an enabling circuit because it can pass X or block X. But there is a little problem that when X is blocked, Y is not specified. The value of Y is not known. So what if we want to have an enabling circuit such that if the circuit is enabled, then Y is X, and when the circuit is disabled, we want to fix the value of Y, either to 0 or to 1. In other words, we want to value fix Y to some value if the circuit is disabled. In this case, when the circuit is disabled, Y is known. It is fixed. It is not affected by X. It is always 0 or always 1. So if I tell you design this circuit, which has two inputs, X and enable, such that, so we have here enable or C, and we have here X, we have here Y. So the combinations are 0, 1, 1, 0, 1, 1. We want to design this circuit such that when the circuit is disabled, Y is fixed to either 1 or 0. Let's assume we fix it to 0. And when the circuit is enabled, in other words, C is 1, we want Y to follow X, or we want X to pass through to Y. So it is like this. What is this circuit? I'm designing this circuit. Somebody told you or asked you to design this circuit. What is this circuit? What is this circuit?
دكتور بنعمل AND من السي والإكس.
Exactly. So this circuit is simply an AND gate. So this is C, this is Y. So look here. If C is 0, 0 and X is always 0. So Y is always 0, even if X is 1, even if X changes. So you disabled X from affecting Y. Okay? But when C is 1, 1 and X is X. So Y is X. So whatever is X, Y will be the same as X. Now at home or later, try to design this enabling circuit such that when C is 0, Y is value fixed to 1. Y is value fixed to 1, and 1, 1, Y is X. What is this circuit?
OR gate دكتور.
It's not an OR gate.
لا مو.
It is
NAND?
NAND? لا ولا NAND. If you draw the K map, this is C, this is X, 1, 1, 0, 1. So it is C bar, right? Or this, which is X. So you need two gates here. You need C bar, you need an inverter, and you need an OR gate. You need an OR gate. So you can design the circuit the way you want, but I want you to get the idea. What is meant by enabling circuit? A circuit that allows X to pass to Y. One straightforward approach to do it is using a tri-state buffer. However, the problem with tri-state buffers that when the circuit is disabled, Y has no value. The value of Y is not known, is not specified, because here we have zeta or high resistance. However, if we want to design this circuit such that when it is disabled, Y is fixed, is value fixed, is constant, is not affected by X, we can go this way, or we can go this way, or some other ways. We can do it in many other ways. But this is the concept that I want you to know, because we will use it later. Okay? So this is the third concept that I want to discuss with you. Any question? All right. So let's now move to other design examples, which are very important, which are commonly used when it comes to designing digital logic circuits. And the first one is, let's see, we have 4.5. 4.5 binary adder. Binary adder. And this is very important operation in computers. If you have two numbers that you want to add, then the first number is represented in binary, the second number is represented in binary, and you want to add them to get the binary result. So this is done by a special hardware called adder, which is basically a combinational logic circuit that should take n bits, let's say this is A, this is B, add them to produce n bits, which is called, let's say, sum. So we want to design a circuit that which is commonly called n-bit. This is called n-bit adder. N-bit adder implies that you want to add A to B, given the fact that both A and B are n-bit. The size of them is n-bit to produce the sum, which is also n-bit. So this circuit is basically a combinational logic circuit that is a function of A and B, which are the two inputs. How will you design this circuit? It is the same approach. It should be the same approach because this is a combinational logic circuit. You know the relation between the output, which is the sum, and the input. So you just put the truth table. However, if you want to follow the same design procedure that we discussed earlier, you will find that it will become difficult as n grows up. Let's say if n is 1, how many inputs you will have? 2 inputs, right? One here. So we have 2 inputs and 1 output. If n is, so you can work with this because you know how to build the truth table for 2 inputs, for 2 variables. Now, if n is 5, so you know you want to add 5 bits with 5 bits. How many inputs you will have? 10 inputs. And what will be the size of the truth table? So if n equals 1, that's fine. We have 2 inputs. If n equals 5, then we have 10 inputs. And what is the size of the truth table? 2 to the power 10. We have 2 to the power 10 combinations, which is 1024. Here, the size of the truth table, simple, 2 to the power 2, which is 4. Like in the computer that you are using now, it is 64-bit computer. So n is 64. Imagine that. N is 64, so you will have 128 inputs, which means the size of the truth table or the number of combinations is 2 to the power 128. So this is very, very large truth table. This is very huge truth table. So how do they design the adder that you have inside your computer, which is 64-bit adder, which adds 64-bit to 64-bit. Designing this adder or this circuit using the approach that we discussed so far is not easy, is not straightforward. You cannot do it. So how can we do that? How do we have such big adders inside our computers? How do they design them? This is very important new concept, and it is based on looking how we perform addition. Let's assume that n equals 4. So we have 2 4-bit numbers, A3, A2, A1, A0 plus B3, B2, B1, and B0. So I will call this S for simplicity. How do you add these 4-bit numbers? We know how to do that from chapter 1. You add A0 plus B0, you will get S0, the first bit of the sum. And at the same time, you may generate a carry. Let's call it C1 because it goes to bit number 1. Then here you add C1 plus A1 plus B1 to get S1. Then you get C2 going into position number 2. You add C2 plus A2 plus B2, you get S2. The same thing you do here, C3, you get S3. And when you do this, you may end up, you get C4, the carry that gets out of this. So if you look at the steps that you do when you want to add these two 4-bit numbers, basically you are doing the same operation at every bit position, right? You are adding one bit to another bit to produce a sum bit and a carry bit. Then when you move to the next position, you add 3 bits, C1 plus A1 plus B1 to get S1 and C2. Then you do the same. You add 3 bits to get this. You add 3 bits to get this. So basically, if I design a circuit that can do this, that can add 2 bits and produce a sum and a carry, then I make copies of this cell and I connect them. I can build whatever adder that I want. I can build 2-bit adder, 4-bit adder, 11-bit adder, 64-bit adder. Basically, by taking the circuit that does this, it adds 1 bit to another bit to produce a bit, and I make copies of it in order to do the rest of the operations. So this is one popular design approach, which is called the iterative approach, or designing iterative circuits, or the circuits that repeat the same operation. It is the same operation repeated over and over. So you don't have to design the circuit all at once. You design the circuit that does the simple or the operation that repeats. Then you create copies of this circuit. You connect them to produce this. So this is very important concept to design what we call iterative circuits, or circuits that perform the same operation over and over, which is basically here adding 1 bit to another bit to produce a bit, and which is the sum, and produce another bit, which is the carry that should be added to the other 2 bits. And this, there are many ways to do it. Let's look at it. So we want basically to design this. So let's start for 4.5.1 half adder. In this circuit, we want to design very simple circuit that takes 1 bit, which is A, that takes another bit, which is B. So this is 1, this is 1, and we get sum as 1 bit, and we get carry as also 1 bit. So this circuit is called half adder. Half adder, and we will see later why it is called a half adder. So we want to design this circuit, the circuit that adds A to B. So basically S is A plus B. This is not OR. I'm writing arithmetic here. So this is A plus B. A plus B. So if I tell you to design this circuit, you will tell me that the circuit has 2 inputs. It is clear, and the output is sum. Let me write them like this: carry and sum. So the inputs 0, 0, 0, 1, 1, 0, 1, 1. 0 plus 0 is 0, and there is no carry, right? 0 plus 1 is 1, and there is no carry. 1 plus 0 is 1, and there is no carry. 1 plus 1 is 0, and there is a carry. So basically, I'm trying to design this circuit, which is capable of adding 1 bit to another bit to produce the sum and the carry. Produce the sum and the carry. So if I want to design this circuit, what is inside this circuit? I have two outputs. What is S? If you look at S here, what is S?
XOR.
It's XOR, very straightforward. If you draw the K-map and try to simplify it, you will end up that it is an XOR. So it is basically A XOR B, which is basically sum of minterms 1 and 2. What is C?
And.
And. This is and. So it is A, B. So basically, this circuit is XOR between A, B, and between A, B to produce sum and carry. So the circuit that can add one bit to another bit is this. So what is inside the box is this circuit. This is an AND gate. Very simple circuit. However, this circuit, it is a 1-bit half adder. It can add 1 bit to another bit only. But what if I want, as we said earlier, to have 2-bit adder or 4-bit adder or 16-bit adder? We simply need to take copies of this and figure out how to connect them in order to perform the required operation. So let's see that through an example. But before we look at the example, do you have any questions? So it's straightforward. It is very expensive and difficult to design an n-bit adder with large N using the conventional approach. Instead of doing that, we looked at the mechanics of the addition operation between two n-bit numbers and figured out that we are basically doing the same operation over and over at every bit position. So why not to design the operation that works for one position or for 2 bits? Then we replicate that circuit or replicate that operation. So let's try before we take the quiz to do this through an example. So let's say design a 2-bit adder. 2-bit adder implies that an adder that adds 2 numbers, each of which is 2 bits. Each of which is 2 bits using half adders and any other gates. Okay, so basically we want to design a circuit, 2 bits, this is A, this is B, to produce a sum, which is 2 bits sum, like this. But we don't want to design it using the conventional approach. We want to design it using the iterative approach, in which we know that we have blocks or circuits that can add 1 bit to another bit to produce sum and carry. So let's start by looking how do we do that on paper. We have 2 numbers, each of which is 2 bits, B1, B0, A1, A0. We want to add them. So we S0, and what we get here is C1, the carry that is going into position number 1. Then we add C1 to A1. Then we add the result to what? To B1 to get S1, and we will get a carry C2 here. So how many half adders do we need to perform these operations? If we start from here, we need a half adder here. So we get a half adder. This is half adder. It will have inputs A0, B0. So if I add A0 to B0, what is the output? The sum is S0, right? The sum is S0. And we have a carry here. And this carry is C1. It is this. The output of this block. I know what is inside this block, and I don't have to show it. If I draw it like this, everybody should know that this is a half adder circuit. So it is implemented using some gates inside it. What is next? If I want to use half adders only, I need next to add C1 to A1, right? So I need a half adder circuit here to add C1 to A1, right? And I will get here some value and a carry. What is this sum? Is it S1?
S1
No, it's not.
هذا السم اللي طلع هون, this sum is basically C1 plus A1, which has to be added to what?
To B1.
To B1. So we have B1 here, and this is, let's say, I will write here A1 plus C1, which I have to add it to what? To B1, because I added C1 to A1 here. Then I need to add the result, which is this. I will write here S and C to indicate that this is the sum, this is the carry. And here I will get S to be what? S1. If I add C1 to A1 to B1, I will get S1. And if this is the carry output, where is C2? Is C2 here or is C2 here?
The sum of both of them.
S0 مع
Is this carry C2 this carry or this carry? Which carry?
The sum of الاثنين.
Sum of
carries.
the name. Basically, if you think about it, this will be OR C2. Why? If I tell you when this C2 will be 1, if you add this one to this one, for example, if this is 0, this is 0, this is 1. Can you get a carry? No. If this is 1, 1, 1, 1 plus 1, which is 1 plus 1, this will be set. Can you get carry to be 1 here if this is 1, this is 1? No. But if this is 0, this is 1, and this is 1, you may get the carry from here. So this C2 might be generated when you add this to this, or when you add their result to what? To B. So the carry C2 is set when there is a carry generated from adding C1 to A1, or from adding the result of A1 plus C1 to what? To B1. So this is very important. Now I can put it in a box like this. Let's say this is S0, this is S1. So in this box, I have now a 2-bit adder that is built using 3 half adders and OR gate. Think about this carefully at home. How can you get this carry to B1 if you add this to this, or when you add this to this? So that's why I translated into an OR gate. There is no way you can get 1 here and 1 here. You can't. Maximum you can have 0, 1 here, or 1, 0 here to get C2 equals to 1. Otherwise, C2 will be 0. Think about it by taking different combinations here, 0, 0, 0, 0, 1, 0, 1, 0, 1, and so on. You will figure out that C2 will be only 1 if this is 1 or this is 1. That's why I ordered them together. So given this, I can put it in a box like this and sell it. I can put it in a box and sell it. I say this is A, which is 2 bits. This is B, which is 2 bits. This is the sum, which is 2 bits. This is C, or for example, C out, which is 1 bit. And I call it 2-bit adder. 2-bit adder. Okay? Think about it at home and try to build a 3-bit adder. As an exercise, leave one page. Try to think of building a 3-bit adder using half adders. And try to approach the problem the same way I did. Write how you do it on paper, B2, B1, B0, and see in order to see how to connect the half adder units and where to find the carry. You will see that you will need OR gates between every 2 half adders in order to decide where is the carry coming from. Where is the carry coming from? So please try to do this at home, 3-bit adder using half adders and OR gates. Basically, you will need OR gates. So when you do that at home, you will see how difficult it is to build larger adders using half adders. And the problem that, with half adders is we design them assuming that we always add 2 bits to produce 1 bit and a carry. We to produce a sum and a carry. However, this is not the thing that is most frequent in the addition operation. A2, A1, A0, B0, B1, B2. When we design the half adder, we assume that we always add 1 bit to another bit to produce sum and carry. But essentially, this is only done at the least significant bit. For the following bits, we essentially add how many bits? 3 bits to produce sum and carry. So our life would have been easier if we designed our circuit such that we always add 3 bits instead of adding 2 bits. Because when we designed the circuit here, we figured out what we needed is a half adder to add 2 bits at the beginning, but afterwards we need to add 3 bits, carry A, B. So this is solved by looking at a different adder, which is 4.5.2, right? 4.5.2, which is the full adder. And the idea of the full adder is to solve the problem of working with OR gates. We needed the OR gate in order to decide where is the carry coming from, because when we designed the circuit to add, we designed it assuming that we are always adding 2 bits, but essentially we are adding 3 bits most of the time. We are only adding 2 bits at the beginning or at the least significant bit. So basically, the full adder is a circuit that adds 3 numbers or 3 bits, A, B, and carry N, Cn, and Cn to produce a sum and carry C out and carry C out. So why do we want to do this? Because as I said earlier, when we add n-bit numbers, for most of the time, we are adding 3 bits. Only at the very first input or the very first base bit, which is the least significant bit, we are adding 2 bits. So if we design our 1-bit adder to be full adder, we can make our life easier when it comes to using this block to build larger adders. So if I ask you to design this circuit, design a circuit that adds 3 bits to produce sum and Cout. How will you do that? Straightforward. A, B, C, N. Let me draw it over there. It is A, B, C, N. And we have Cout, and we have sum. So we want to add 0 plus 0 plus 0. The sum is 0, Cout is 0. 0 plus 0 plus 1, it is 0, 1. The sum is 1, there is no carry. If you add 0, 1, 0, 0, 1, 1. 0 plus 1 plus 0, it is also 1, there is no carry. 0 plus 1 plus 1, it is 1 plus 1 is 0, and there is carry. 1 plus 0 plus 0 is 1, 0. Sorry. 1, 0, 1. 1 plus 0 plus 1, it is 0, and there is carry. 1 plus 1 plus 0, which is 0 and carry. And lastly, 1 plus 1 plus 1, which is 1, and there is also carry. So basically, I'm just adding the 3 bits. 1 plus 1 plus 1 is 3. 1 plus 1 plus 0 is 2. If you want to look at it this way. 1 plus 0 plus 1 is 2, and so on. So we have the truth table.
يعني دكتور
Yes.
بتعمل or بين ال A وال B بعدين تجمع لهم ال C.
لا I'm adding مش oring. I'm بحكي أنا 0 plus 0 plus 0. 1 plus 1 plus 1. 1 plus 1 plus 1.
1 no carry 1.
1 no carry 1. Yes, there is no or. I'm adding them. Because this is the relation between the input and the output. The relation is basically adding the 3 bits to get sum and Cout.
تمام.
So now if you want to simplify, this is sum, this is Cout. What is sum? Sum هيو 0, 1, 1, 0, 1, 0, 0, 1. Right? So this is the sum. Can you simplify? You can't combine ones. So what is this essentially? Sum is basically sum of minterms اللي هم 1 و2 و4 و7 اللي هو مين هدول؟ What's this? XOR A, XOR B, XOR Cn, which is the same as the half adder. The sum output in the half adder is also XOR between A and B, but now we have XOR between A, B, and Cn. How about Cout? Cout is 0, 0. If you fill the map, 0, 1 here. Then we have 0, 1, 1, 1. So this is A, this is B, this is Cn. So we have this prime implicant, this prime implicant, and all of them are essential. So Cout is basically A and Cn, B and Cn, or AB. This is AB, this is B and Cn, this is A and Cn. So this is the circuit that can add 3 bits to produce a sum and carry out. And next time we will see how to use this circuit, how using this circuit. Leave some space and draw the logic diagram of this circuit, put it in a box, and it will be this circuit that we wanted to design. Next time we will see how to use this to build a bigger adder, 2-bit adder, 4-bit adder, and you will see how it is easy to do it using full adders. It's much easier to do using full adders. Okay. So why did we move to the full adder? In order to make it easier to build larger adders. Instead of working with OR gates and half adders, we just work with full adders. Okay. Any question? طيب. Let's now go to the quiz. As I sent you